Welcome to this explainer where we're going to unlock the secrets hidden in your data. Think of hypothesis testing as the ultimate data detective's toolkit. We live in a world just drowning in data, right? But raw numbers, they rarely tell the whole story on their own. We actually have to interrogate that data to find the truth hiding beneath all that random variation. And why does this matter to us? Well, misinterpreting data can lead to absolutely disastrous business decisions, misguided public policy, or even false medical claims. To find the real truth, we need a highly specific set of statistical tools. So, this brings us to the fundamental question of our entire investigation. How do we mathematically prove that two things are actually different? I mean, whether we're comparing the durability of two competing floor waxes or testing a brand new medication against a placebo, we can't just look at a tiny numerical difference and call it a day. No way. We need the right statistical tool to separate random chance from reality. Here's the agenda for today's explainer. First, comparing two population means. Second, comparing two proportions. Third, independence and correlation. And fourth, comparing multiple means using ANOVA. Let's get into it. Section 1. Comparing two population means. Okay, let's open up the first compartment of our toolkit. Imagine you're a detective hired to prove which of two competing floor waxes actually lasts longer. You randomly apply wax 1 to 20 floors and wax 2 to another 20 entirely different floors. Since the floors testing wax 1 have absolutely no relationship to the floors testing wax 2, we call these independent means. Our main question here is the average lasting time truly different? Now, the critical detail here is how our available data dictates our mathematical weapon of choice. If we magically know the population standard deviations, which, spoiler alert, you almost never do in the real world, we'd use a normal distribution and what's called a z-test. But in reality, standard deviations are almost always unknown. So we usually rely on the Aspen-Welch t-test, which utilizes a student's t-distribution. And there's a really critical rule here. We purposefully do not pool the sample variances when calculating this. But what if our two sets of data aren't independent? Like, what if we're testing the exact same patients before and after a specific treatment, like hypnotism for pain relief? Well, that changes everything. We can't treat the before scores and after scores as independent groups, because obviously they come from the exact same person. In this case, we have to use a tool specifically built for matched or paired samples. When we're analyzing matched samples, the actual data we test isn't the individual before and after scores. We actually just ignore those entirely. Instead, the real data is the calculated difference between them. We take the after score, subtract the before score, and we run our entire hypothesis test on those specific differences. We're looking to see if the true mean difference is less than 0, which would mean, yep, there was a real drop in pain. So let's look at the results. By running a student's t-test on those exact differences, our hypnotism example yields a p-value of 0.0095. Now, in our detective work, the p-value is basically the probability that we'd see these results purely by random chance if the hypnotism actually did nothing at all. A p-value of 0.0095 is less than 1%. That is well below our standard 5% significance level. It's a tiny number with massive implications. Case closed. Because our p-value was so incredibly low, we reject the null hypothesis. Remember, the null hypothesis basically claims, hey, nothing happened here. We throw that right out, and we reach a mathematically sound conclusion that the hypnotism was indeed effective at lowering pain measurements on average. Section 2. Comparing two proportions. Often we don't really care about the average of something. We care about how often a specific trait occurs. For example, say a marketing firm wants to know, do younger adults really own electric vehicles at a greater rate than older adults? When we're asking questions about the rate of an occurrence between two distinct groups like this, we're dealing with independent population proportions. To actually run this test, we have to pretend for a moment that both groups are exactly the same. Because our null hypothesis assumes the two proportions are equal, we dump all the data into one big bucket to find what's called a pooled proportion. Basically, we add up all the EV owners together and divide that by everyone surveyed. This pooled number then becomes the anchor for our normal distribution test. So in our electric vehicle study, analyzing a 10% adoption rate by young adults versus just 5% by older adults resulted in a super tiny p-value. That means we easily reject the null hypothesis, mathematically proving that there is a significantly larger proportion of younger EV owners. Section 3. Independence and correlation. All right, now we need tools to solve mysteries about relationships. Are two factors completely independent, or are they connected? Take this real-world puzzle. Is getting a speeding violation independent of using a cell phone while driving? To find out if categorical variables like these are related, we evaluate a contingency table. We map out our observed real-world data, so how many people actually sped while on the phone, and we mathematically compare it against the expected values. These expected values are the exact numbers we'd expect to see if the two behaviors had absolutely nothing to do with each other. We evaluate this using a test of independence. This is a right-tailed chi-square test, and it will show a massive test statistic if your observed real-world data is far off from what those independent expected values should look like. If that test statistic is huge and your p-value is tiny, boom, you've caught the variables in a relationship. You reject the idea of independence and conclude that cell phone use and speeding are, for sure, dependent. Now, to test numerical relationships, like maybe predicting a final exam score from a third exam score, we look for the correlation coefficient, also known as rho. It's a pretty simple, systematic process. First, we state our null hypothesis, which assumes no correlation exists. Second, we calculate our test statistic. Third, we find our p-value. And finally, we make our decision to either reject or not reject that hypothesis. The ultimate goal here is to prove that our sample correlation coefficient, which we call R, is significantly different from 0. If it is, we have a significant correlation. That gives us the absolute green light to use our regression line for future predictions. But if the test shows our correlation isn't significant, that means R is just too close to 0, our line is useless, and we absolutely should not use it to predict future outcomes. Section 4, Comparing Multiple Means, ANOVA. For our final section, we're looking at the absolute ultimate investigative tool. We've talked about comparing two means, but what happens when the mystery in front of you involves 3, 4, or even 5 different groups? Enter analysis of variance, or ANOVA. This is a brilliant statistical workaround. Instead of trying to compare every single mean directly to every other mean, which, trust me, gets messy really fast, a one-way ANOVA analyzes the variances, or the spread, of the combined data to determine if multiple group averages are actually equal. ANOVA operates on a very strict baseline. The null hypothesis for ANOVA is that every single group mean is exactly the same. Whether you have 3 groups or 30, the assumption is that any slight differences you see in your samples are purely due to random variation. If the variance between the groups is significantly larger than the variance within the groups, ANOVA tells us to reject this null hypothesis, meaning at least one group is mathematically different from the rest. But you have to be careful. ANOVA is a heavy-duty tool, and it requires a really stable foundation. You can only wield the power of a one-way ANOVA if your data strictly satisfies 5 assumptions. Your populations have to be normal, your samples must be random and independent, the standard deviations have to be equal, your testing factor must be categorical, and your response has to be numerical. If you violate any of these, well, your whole investigation crumbles. We've definitely explored quite a bit today, from testing simple differences in floor walks to proving the correlation between exam scores, and even utilizing the brilliant variance analysis of ANOVA. Now that you understand how to navigate this incredible statistical toolkit, the true test begins. Look around at the claims, the studies, and the headlines you see every single day. Are they using the exact rate tool for their data, or are they hiding behind bad math? Keep questioning the data, folks. Thanks for joining me on this explainer.